sorry, the video cut out there for a second. So we did atomic radius, which was how big the atom is. And it's a measure of small to big, going from sort of up by the fluorine and things like that, and getting bigger as you go down towards francium and cesium and things like that. Then ionization energy. So I don't think we got quite to this. Ionization energy is the amount of energy needed to remove one electron. So remember, ionization is when you get a charge on something, so it's the amount of energy needed to remove one electron. And the periodic trend goes from small, and it increases as you have fewer shells, because it's harder to remove an electron as it gets closer to the nucleus. And from right to left, because the Zeph is increasing. And remember, there are some periodic trends that include the noble gases and some that do not. So ionization energy does. So we're going to just make a note here that it includes the noble gases. Then we have electron affinity. Electron affinity is the amount of energy released when an electron is added. So an amount of energy released when one electron is added. So the periodic trend is going to increase. So the electron affinity increases as you have fewer shells, because you have electrons being closer and closer to the nucleus. So when you add an electron, it helps them to relax more. It also gets bigger as you go from right to left, because the Zeph is increasing. But this one does not include the noble gases. So the noble gases have a full stable octet. They don't want another electron. So it's not going to be in a lower energy state when you add an electron to it. So the noble gases are 0. They are not part of the trend. And the very last one is electronegativity. Don't forget, you have your electronegativity periodic table on the back of your periodic table that shows the electronegativity of each element. And so electronegativity is an atom's ability to attract electrons. And the periodic trend it's going to increase as you go up, because there's fewer shells, you're getting closer to the nucleus, so the positive charges can pull in the electrons. And from right to left, because the Zeph, so that's the effective nuclear charge, is increasing. Except, again, the noble gases are 0, because they do not want any more electrons. Are 0. Okay, so as just a little note, for all of these trends, when we're talking about going from right to left or left to right, we're looking at the effective nuclear charge. So we're going to make a little note here for all of these things. So effective nuclear charge is low by the alkali metals and high at the halogens. Okay, across the row. So it increases from low to high across rows. And then when we talk about sort of the up and down piece, we're looking at the number of shells, which increases as you go down in columns. Pardon me. Okay, so next we're going to look at ionic versus covalent compounds. So over here, ionic versus covalent. And we're going to write down some properties. So this is back to that lab that we did where we were comparing ionic and molecular compounds. So an ionic compound is a metal and a nonmetal versus covalent is nonmetals. In ionic compounds, the electrons are transferred from the metal to the nonmetal to form ions, which then attract. But in covalent, the electrons are shared between two. Ionic compounds have high melting points. And solubility in water. And conductivity. Whereas covalent compounds have relatively low melting points, solubility, and conductivity. Next, we're going to look at drawing Lewis diagrams of compounds. So we're going to look at one example here. We're going to do ammonium, so NH4+. If you remember back when we did this in our notes, if you need more practice, look back in your notes. There's tons of different molecules to practice drawing. And you might want to remember that my favorite one is carbonate. It's my favorite polyatomic ion. So you might see that one on the exam, hint, hint. So we want to keep in mind here with ammonium, because it's got a positive charge, it's an ion. The positive charge means that we've removed one electron. So we start by drawing the Lewis dot diagrams of each of the elements. So we've got a nitrogen, 1, 2, 3, 4, 5. And then we've got 4 hydrogens. So 1, 2, 3, 4. And now we can pair up unpaired electrons. So pair up one there, one there, one there. And then we have one spot that's not filled, but remember we have to remove one electron. So one of these 2 nitrogen electrons we're going to remove to get that positive charge, and then we can pair up those 2. So now we can draw the ion, and we can turn our bonding pairs of electrons into dashes. So we'll get N with 4 H's on it. And remember, because it's an ion, we need to include brackets and write the charge in the top right corner. When you're doing compounds that have negative charges, again, you'd be adding electrons instead of removing, and you'd show the charge on the top. If you're using a compound that has other valence electrons, so say instead of hydrogen these were chlorine or something like that, then you need to make sure that you show the lone pairs. So we'll make a little star here. So don't forget lone pairs. All right, and the last topic in this unit was polarity. So with polarity, remember to check your table of electronegativities on the back of the periodic table. So use the table of electronegativities. And there's a couple different pieces that go into showing polarity. The first one are partial charges. So partial charges show the difference in electronegativity within one bond. So for an example, if I have a carbon and a hydrogen, the carbon is more electronegative than the hydrogen, so the electrons in this bond are going to spend more time around the carbon, which is going to give it a slightly negative charge, and the hydrogen a slightly positive charge, because you're checking the electronegativity in the table. So the electronegativity of carbon is 2.5, and the electronegativity of hydrogen is 2.1. So there's a slight difference. The electrons spend more time closer to the atom that has a higher electronegativity. So the partial charges are those little delta minus and delta positive. And you can show those for all the different bonds in a compound. And then we can show an overall molecular dipole, if there is one. So for example, if I look at H2S, so there's my compound, and I have 2 extra sets of lone pairs on the outside. When I'm looking at my electronegativities, the electronegativity of sulfur is 2.4. And then hydrogen is 2.1. Is 2.1. So the electrons in these bonds are going to spend more time near sulfur, and that's going to give this molecule an overall molecular dipole. So we show it with an arrow where the pointy end is the negative end and the positive end with the little cross is positive. So we can even write that over here as a little legend. So there's how you show the dipole. This end is positive, and this end is negative. Sometimes you'll come across molecules that will have partial charges, so they'll have a difference in electronegativity, but they won't actually have an overall dipole. So an example of that would be carbon dioxide. So the electronegativity of the carbon is 2.5, but the oxygen is 3.5. So this is 3.5, and this one is 3.5 as well. But because they're both pulling out in equal and opposite directions, there would be no overall dipole in this molecule. If on the exam there's one that has no dipole, don't just leave it blank. You won't get it right. You need to actually write something saying that you know that there is no overall dipole. Okay, so that's unit number 2, and again on your in-class review practice questions, there's a page of practice questions for these types of questions. Please complete those while it's nice and fresh in your mind, and we'll look at some of that stuff next class.